Okay, so let's start today's lecture. So for the assignment, I updated the web page. What's wrong? Ooh. So my computer is just frozen. So let's yeah. So for the assignment, I put the assignment document and Python files in my GitHub. So here's the instruction. And for the files, I put both Python files in IPython notebook. You can copy it to your own Colab. So the first file is the PID control straight line from with Twiddle for PID controller tuning from Udacity. So you can run it. And it gives you the final Twiddle error and the plot of the reference trajectory, which is the straight line, a red straight line, and the green trajectory, which is the vehicle's trajectory, vehicle's path traveled. So there's an initial oscillation, but it converges to the reference trajectory after a very short, over 25 steps. So the code, so the class robot is provided by Udacity. So it initializes a robot with the XY position, orientation, and so on. And the move operation, first it clips the steering angle to be within a lower and upper bound, and then applies some drift. And then this is the kinematic bicycle model we discussed in class. If the angle is very small, then you apply the straight line motion. If the angle is large, then you use the accurate description of the bicycle model to compute the next position. So make robot, just instantiate the robot and run up a method, runs for n time steps, n equals 100 here. So and appends every position along the trajectory into two Python arrays, XY trajectory, and Twiddle choose the PID parameters. The P data structure contains proportional derivative integral, the three parameters to be tuned. DP is the initial step size. Initial, so you adjust the parameter by DP at every time. So DP is the initial step size direction, step magnitude for adjustment. But it may be updated in the Twiddle itself. So it may be enlarged or decreased depending on the error situation. So we explained this part in class. You can review last time's lecture. So this is essentially a gradient descent. So the dp can be viewed as the learning rate. And first you run Twiddle to tune the PID parameters, and then make robot and run it with the given fixed PID parameters. Then you plot XY in this figure. So I don't know why it plots another empty figure here. So from the code, it seems there should be only a single figure. If someone figures it out, someone knows it, let me know why it's drawing two.
I think it has two X's, right? You're creating subplot of two rows.
I think in the PIT.subplot, maybe if you change it to 1 instead of 2, I think it's it dots
If you
two
remove
rows.
it, yeah, exactly. If you remove AX2 should be removed too. AX2 should be gone.
No, if you have 1, it doesn't work. So
just remove the X2.
AX2 has to be removed. Yeah.
Oh,
X2 has
AX2. I
Yeah.
see.
Yeah.
No.
Oh, cool. Okay, that's good. So yeah, I'll update this on my GitHub. So let me do that. So the Twiddle error is very small. First, it's because for the straight line, it has perfect tracking after the initial transient period. Second, the number of time steps is only 100. So so the next file is the PID control racetrack file. So now it had a racetrack shape, not a straight line anymore. So so the main difference lies in the CTE function, cross-track error. So you need to compute the cross-track error depending on where you are. So if you are in the left or right end of the track, then you compute the error based on the two half circles. Otherwise, you compute it. So the top if statement describes when you are in the middle of the track. So in the middle position, so yeah, in the center position, the cross-track error is the perpendicular distance from the top or bottom portion of the track. But if you're on both ends, either end of the track, then you need to measure the distance to the center of the circle. So that's what this function is doing. So if y is greater than radius, then it's outside of the circles. Then you compute CTE. So it's outside of the track. So X describes where either you're in the middle part of the track or on the left end or right end. Y describes your Y position. So either outside of the track or inside of the track. So the assignment asks you to first add in the function twiddle to the tune controller gain parameters automatically. That is, you take the twiddle function from the first file and copy it into the second file. And you may have to adjust some minor things, but the purpose is to tune the controller parameters. Then you need to change the track shape to a round circle instead of the middle square plus 2 half circles. So in this step, you need to modify the function CTE, cross-track error, to compute the distance from the track. And then task 3, you need to increase the vehicle speed. So if you increase it too much, it may lose control, giving you a trajectory like this. So you need to either increase the track length or reduce the time step size. So in this assignment, you reduce the time step size. So in the PowerPoint, there's one slide that's not mentioned in last year's video. Yeah, so the Python code assumes a controller time step size DT is 1. So for general DT, you need to modify the move to have input parameters be times DT. And in PID control law, you need to add a DT here. So divide and multiply by DT. So in the Python code, there's no DT because it's 1 by default. So so that's the 3 tasks for this assignment. Any questions?
Do we need to write a report on it, or it's just a programming assignment only?
You need to write a short report, as I said here. Submit a report and corresponding Python programs describing. So for task 1, include the gains and error visualization. Actually, this can be done in the Python code, IPython notebook. Yeah, some visualization. So in fact, you can run the IPython notebook and print out the whole notebook. That's fine.
Okay, yeah.
Yeah. Okay, so let's start a new lecture on planning. So I just updated the lecture slides this morning. So please download the latest version. So planning has a hierarchy of different levels. At a high level, you have mission planning. That is map level navigation. In the middle, you have behavior planning. That is to choose a behavior based on environmental conditions. And at the lowest level, you have a motion planning. So which includes path planning and speed profile generation along the path. So it generates a reference trajectory to be tracked by the downstream controller, which we discussed in last class, could be PID or MPC. So each planner gives output as input to the next level planner. The mission planner takes as input the current goal, the desired detailed roadmap and vehicle position, and generates a mission path. And behavior planner generates a behavior constraints. A local planner generates a reference trajectory to be tracked by the controllers. So here's another view of the multiple levels of planning. I took it from this paper down here. So the route planning is essentially Google Map level planning. You need to select a route from your home to your office, for example. Behavior level, you need to switch between different behaviors. So the route planning generates a sequence of waypoints through the road network that is going through which intersection and travel through which direction. And behavior layer has its finite state machine. Parking maneuver, lane following, negotiate intersection, change lanes, and unstructured environments, and so on. So it generates a motion specification as input to the motion planning, the lowest level of planning. So it generates a reference path, perhaps for passing a vehicle, for example. And also a speed along the path to be provided as input to the next level controller. Feedback control could be PID or MPC. So route planning is to find the optimal path for navigation from start to goal on a weighted graph. So here's an example. You want to travel from a start position, could be a home, to the end position in your office. So the weight could be the length of each segment, could be the travel time depending on congestion levels. So we use graph search algorithms. For example, a Dijkstra's algorithm or A star to perform the graph search efficiently. So let's first briefly discuss the breadth first search and depth first search, two very basic graph search algorithms. So breadth first search, at each node expand all neighbor nodes at the present depths prior to moving on to the nodes at the next depth level. So for this graph here, you traverse the nodes in this order. So it's called breadth first, because you are traversing all the neighbors of a node before moving on to the next layer. So depth first search. So at each node expand as far as possible along each branch to the very end of the graph, a leaf node, and then you backtrack to the next level and traverse to the leaf of the next branch. And then you backtrack, traverse, and backtrack, traverse, and finally you finish. So both of these search algorithms are inefficient since they do not consider edge costs for selecting the next node to be expanded. So BFS is better than DFS because it can finish after finding a path to the goal with total cost less than or equal to the cost of all other partial paths. And whereas DFS must expand all nodes of the graph. So they're not really used for robotic path planning today. It's shown here mainly for comparison purposes. So here's a running example. You have a start position S and a goal position G. And you have weights on the edges. So the shortest path is this path with length of 22. The other path has length of 25. So for BFS, you initially go towards A, and then B, and then C, and then A, B, C. Yeah, the red color indicates the frontier. So
A and then C, I think.
I'm sorry?
So S to A and then S to C.
Right.
Right.
Yeah, in this order. So yeah, okay. Yeah. A, C, B, G. Yeah, that's it. So notice that at this position, you cannot finish because you must expand C because the total cost is higher than 10, which is the cost of the other partial path through C. So at this point, you have seen a path of length 25. So the other partial path has length 10. So you're not sure if the other partial paths can be further traversed to have a lower total cost. That's why you need to continue until the very end. So for DFS, you go first to A, and then B, and then G, and then backtrack C, and to here. So now you have expanded all paths and found out this shortest path is 22 SCG. So both of these search algorithms do not consider the edge cost, edge weights during the search, so they're inefficient. Dijkstra,
excuse me.
Yes.
You're still using a small dot that is very difficult to follow. Could you try to use something else or bigger dot or circle?
Yes, yes. The bigger dot has a problem is that you cannot really draw anything, but that's okay. Yeah. So Dijkstra's algorithm is a more efficient way of searching because it takes into account the edge costs. So it traverses the lower cost edges first and is more efficient in finding the shortest path. So the open array is sorted array sorted stack that's popped in decreasing order of the cost of the partial path to the source node. So if while the open data structure is non-empty, you pop a node off it. If it's go, then you have found the path. Otherwise, you expand the successors and by selecting from the lowest cost next position, next node. So if the U cost, the node cost plus the next edge cost is less than or equal to the open V, the lowest cost, then you set this to be the lowest cost, and otherwise you push it to the stack. So I hope I have an example to illustrate this clearer than the code. So so you start from the start position, start node S, and the next node you expand is A, because the from S there are two edges, to A with cost 2 and to C with cost 10. So you select the shorter one. So at this point, S is blue, indicating that it's a closed set, whereas A and C are in the open set. So they are the frontier of exploration. So at this next step, A has one neighbor, one next downstream node of B. So you place B in the table, and now A is closed, B is open. So and the table is sorted by cost. So now B is ahead of C because B has a lower total cost of 2 plus 3 equals 5. So now you select the lower cost node to expand. So you expand B, which has a cost of 20 to G. So now you place G in the open table and place B in the closed set. So now G has a cost of 25 all the way from S to G, whereas C has a cost of 10 from S to C. So this is a sorted list. So G is behind C in the table. So now the next node to be expanded is C, because it has a lower cost to S. So now you get the 22 to G. So now you have reached G from two different paths. From the top path, you have 25. From the bottom path, you have 22. So the 22 is put in the table to replace the 25. So now S, A, B, C are all closed and G is open. So because G is the target, is the goal node, you have finished. The algorithm has finished. So extract path, it yields the shortest path from the source to G with the length of 10 plus 12 equals 22. So if you there's another algorithm called A star, which is very similar to Dijkstra's, and both are used pretty often in path planning. So the difference is that in Dijkstra's algorithm, the open array is sorted and popped in decreasing order of U cost plus UV cost, which is U cost is the cumulative cost to the current node U, and UV cost is the edge cost of the next edge. So the sum is the cost of the partial pass from the source node to V. Whereas for A star, you have an additional heuristic function H for estimating the cost to go from the V to the goal node. So it's an estimation, but it has to be a conservative approximation. That is, the estimated cost must be less than or equal to the actual cost to go. It's called a admissible heuristic. So with this admissible heuristic, A star can be more efficient than Dijkstra's. So the overall structure of the algorithms are pretty much the same, except for the additional admissible heuristic H. So if H is constant 0, then A star just becomes a Dijkstra's algorithm. So here's an example of A star. So at the source node, we estimate the cost to go to be 11.5, which is less than the actual 22. 22 is unknown, so we're just making an estimation. So
Excuse me?
yes?
You didn't explain, or there's nowhere mentioned how do you make estimation? What is the rules?
Oh, I think I have there's the rules in the in here. So let me explain this first. So in the Wheelie graph representing the road network, the edge cost may be travel distance or travel time, taking into account factors such as speed limit, traffic congestion level, and so on. So if the objective is to minimize the total travel distance from start to goal, then the edge cost is the travel distance between two locations. The H can be set to be the straight line distance to the goal. So it's guaranteed to be admissible heuristic because a straight line is the shortest distance, whereas the road network is not a straight line. So HV is guaranteed to not exceed the actual travel distance. If the objective is to minimize total travel time from start to goal, then the edge cost is travel time between two locations. So we can set H to be the straight line distance to go divided by the maximum speed limit. So assuming that the driver respects the speed limit. So this is the shortest possible amount of time it takes you to travel from the start to goal. So again, it's admissible heuristic because this H will never exceed the actual cost to go. So it's a conservative yet safe estimate. So given this, of course, this estimation, the closer it is to the actual cost to go, the more efficient the algorithm is. If you take a trivial H equals 0, maybe you have no knowledge whatsoever about the future, then you just get Dijkstra's algorithm. But if you have some knowledge, then you should exploit the knowledge to improve the efficiency. So given this H function, we can utilize it to make the search more efficient. So suppose H is 11.5 at this point, and you expand the next two nodes, A and C, as before. So for node A, you have H A equals 22.5, which is okay. It's admissible because it's less than 23, the actual distance. And HC has the heuristic cost to go of 10.5. So now you have another column in the table for estimated total cost, which is the cost to go plus the cost to the source. So it's the for C, it's 10 plus 10.5. For A is 2 plus 22.5. So it's 20.5 and 24.5. So now C is the lower cost node. So you expand C first. So when you reach the have a typo here. Should be G. So when you reach node G, you are at the destination. So the cost to go is 0. Now you know there's no estimation. It's exactly 0. And for A, you have estimated cost to go of 22.5, and the already cost to go for cost to the source of 2, which is the total cost is 24.5. So you don't have to expand the downstream of A anymore. You can stop here and return the shortest path SCG of 10 plus 12, which is equal to 22. So you can see why you can stop here, because the estimated cost going through A must be greater than or equal to 24.5, assuming the heuristic is admissible. So, but you have already found a path with total cost, exact cost of 22 SCG. So there's no point. There's no reason to expand to search further going from node A. So any questions? So, but one caveat, one important condition for A star to work is to have an admissible heuristic. So suppose your heuristic is not good. Suppose you have an inadmissible heuristic. So here, suppose from C, you made the estimate of cost to go of 15.5, which is larger than the actual cost to go, 12. Then you may expand A to get to B, and then you may find a path SABG, which is incorrect. It's not the shortest path if you have a wrong heuristic due to overestimation of the cost to go from node C. So after finding the path SABG with length 25, we incorrectly ignore the other path through C, since its estimated total cost 25.5 is more than 25. So here are some arguments. If the heuristic is admissible, then we can either directly find a path SCG and correctly ignore the other path ABG, or we may go expand. We may find the path at SABG first with length 25, but then we must continue to expand node C to find the correct shortest path SCG, because the estimated total cost of 20.5 is less than 25. So there's a chance of a shorter path going through C. We cannot ignore C. So in summary, if the admissible heuristic, with the admissible heuristic, if you find a path to the goal with exact cost less than or equal to estimated total cost of all the other paths, we can finish and safely ignore all the other paths. Since the actual cost there, the other path's actual cost must be higher than V, than what we have found. So with inadmissible heuristic, then this may not hold true. So even if we find a path to go with exact cost less than or equal to the estimated total cost of all the other paths, we cannot finish and safely ignore all the other paths because their actual cost may be lower than or higher, lower or higher than V. We just don't know. So the key to A star is to design a safe yet a tight estimate for the cost to go H. So here are two very safe methods for estimating H. But if you have additional knowledge, say you know from H, from the current position to the goal, you know the shortest path through the road network, and then you can use that as your shortest distance instead of the straight line distance. So here's an exercise for you to work it out. So in parentheses, you have the Cartesian coordinate of the node. So suppose you have XY coordinates. And then on the edge you have the costs. So starting from S to T, you may try to find the shortest path with Dijkstra's or with a heuristic function h as the straight line distance to go. So for example, from A to T, you may compute the h, the cost as say from A to T, it's the straight line distance is 4 minus 1 squared plus 2 minus 2 squared and square root based on the coordinates. So A star versus Dijkstra. Here's an example, a grid map where the red crosses denote obstacles and the green circles denote the explored positions. So for A star, starting from the source, this position, to the target, assuming a pretty good heuristic, so it can explore much fewer nodes than Dijkstra's algorithm. So Dijkstra's algorithm explores in every direction and less efficient, because if you have no knowledge of the cost to go, then you have to explore pretty much the whole quarter, all these positions. You never know if there may be a shorter path in some other portion of the graph. Whereas if you have a good heuristic function, your search can be much more focused. So here's the animation. Dijkstra essentially expands in a circle and gradually expands. So A star has finished before Dijkstra. So especially when you are at this point in A star, now the search, it becomes extremely fast, because at this point, your heuristic is very, assuming your heuristic is the straight line distance to the goal, then your heuristic is very close to the actual cost to go. And you can prune, you can ignore a lot of other paths and pretty much go straight. Not exactly straight, but go relatively straight to the goal from this point. So from the other positions, because you have the obstacles in the middle, your estimation of the cost to go is not very tight. So the path pruning is less effective. But once you reach this, when you have line of sight to the goal, and then it's very fast. So this Python robotics is a very good package of open source Python code for many algorithms in robotics. So I highly recommend this software package. Yeah, from mapping, localization, path planning, and so for path planning, it has pretty much all the algorithms that's popularly that's in use today. You can find in this software package. So now let's move down one level to examine behavior level, behavior planning. So you plan a set of high-level driving actions or maneuvers to safely achieve the driving mission under various situations based on rules of the road, traffic lights, stop signs, static objects such as parked vehicles, dynamic objects such as moving vehicles, cyclists, pedestrians, and so on. So for dynamic objects, you need behavior prediction. That is where is the other object is going to move to in the near future, which I did not discuss in this class. But there are a huge variety of algorithms for making behavior prediction. For driving maneuvers, it may be a track speed. That is maintain current speed consistent with the other vehicles on the road. For example, cruise control, or just manually tracking the other vehicle, keeping consistent with the other vehicles in the city road. Follow leader, it means match the speed of the leading vehicle and maintain a safe distance. So, well, this is cruise control, where track speed is more of a looser version of cruise control, where you're keeping track of all the vehicles around you, not to be too slow or too fast. Decelerate to stop. So begin decelerating and stop before a given space. Could be a traffic light, could be a stop sign. So stop is to remain stopped in the current position, or change lanes, or turn left, right, U-turn, or a pass. A pass is a complex maneuver involving changing lanes, passing, and optionally changing back to the ego lane. So there are several methods for behavior planning. One is finite state machine based. For example, here you have 3 states: stop, track speed, and decelerate to stop. So you may transition from stop to track speed. That is, you just the light has just turned green from red, or you just stopped at a stop sign and just restart it. Or you can go from track speed to decelerate to stop if you see a stop sign in front, or you may stop, go into stop. So for rule-based, you may have a set of logical statements with priorities. For example, rule 1 says a green light at intersection, then you go drive straight. Rule 2 may say if there's a pedestrian in the intersection, then you stop. So the rule 2 has higher priority than rule 1, that overrides rule 1. So if a pedestrian runs a red light, you should yield. You should stop, despite that you have the green light. So another method is reinforcement learning based. So you learn from trial and error to maximize cumulative reward. So whereas the other two, FSM and rule-based, are all designed by human experts, so with their limitations, where our approach is more flexible, and potentially can be more powerful. So here's an intersection scenario with dynamic objects. So you have a four-way intersection, two-lane road in each direction, and stop sign in every direction, and no other than dynamic objects. So you discretize it into approach zone, the red boxes, that is when you're approaching the intersection, at zone, that is the green boxes, that is when you are at the intersection, and on zone, that is the orange box, that is you're traversing, you're on the intersection. So the size of each zone is determined by ego vehicle speed and size of the intersection. So if the speed is faster, then you should have a longer red box. So here's a simple scenario of an ego vehicle traversing the intersection. So the vehicle starts in this position. It's in the track speed state. That is, it's traveling at constant speed. And then when the ego position equals approaching, that is the driver, either human or the cameras, sees the stop sign. Then there's an event approaching, position equals approaching, which triggers the transition from track speed to decelerate to stop in the red box. So it's decelerating gradually. And when it reaches the green box, it should transition into the stop state. So the transition trigger is ego velocity equals 0 and position equals at. That is, the vehicle is at the green box, at the intersection. So now it should be fully stopped. And while in the stop state, when the stop time is greater than or equal to 3 seconds, it means that it stops for at least 3 seconds. Then it can transition into the track speed state again. That is, it can restart and keep going. So it's a very simple finite state machine for going through an intersection. To make the state machine more robust to noise in state estimation, you may change the ego velocity equals 0 constraint into ego velocity less than or equal to stop threshold. So that is, the velocity estimate may be a noisy estimate based on common filter and other sensors, which may not be exactly accurate. So to leave some margin to noise, you can set up a threshold of stop threshold for ego velocity instead of 0. So notice that in the finite state machine, there's no transition from decelerate to stop to track speed. So that is, you have this transition from here to here, but not from here to back to track speed. So it's because it's an intersection with stop signs. So vehicle must come to a full stop at the stop sign based on traffic rules. So yeah, especially if it's an autonomous vehicle, this should be programmed into the vehicle. Well, if it's a human, of course, it may not be true. So for an intersection with traffic lights, there should be such a transition back from decelerate to stop into track speed, because the light may turn green while vehicle is decelerating. So you can just go through without fully stopping. So so in the previous example, there's only a single ego vehicle. There's no other dynamic objects. So suppose you have some other objects, say some other car in the scenario, then you may add additional state, follow leader, in addition to the three states we saw before. So when another vehicle is in front of the ego vehicle, so you may follow leader. from track speed, you may decelerate to stop directly, go into decelerate to stop, or you may go into follow leader first, and then from follow leader to decelerate to stop, depending on the front vehicle's position and speed. Again, it's a stop sign scenario, so there's no transition back from decelerate to stop to track speed, since the vehicle must come to a complete stop at a stop sign. So you may handle multiple scenarios with hierarchical finite state machine. So you may have a finite state machine for the intersection scenario. You may have another finite state machine for the drive lane scenario. That is, you're driving in the lane on the road. So you may switch between them. Each one may be a superstate in a higher level finite state machine. So each superstate contains a lower level FSM for the scenario. So in the lower level FSM, you may have entry transitions from the outside, from the other state, either going into follow leader or going into track speed, and exit transitions from either follow leader or track speed outside of the superstate. So this allows you to have more compact representations of the FSM for for multiple scenarios. So if you put everything in a single flat FSM, the states may be there may be many states, and the FSM becomes very messy. But with a hierarchical organization, you can have more compact representation.
Excuse me?
Yes?
I don't see any difference between those two scenarios.
Well, from the picture, you see no difference, but in the details, there will be differences. So on the higher level, indeed, they both have the 4 states, but the triggers will be different. So, for example, for example, you may go into stop if your front vehicle is stopped in the drive lane scenario, instead of a stop sign, seeing a stop sign. So
okay, but then
yeah.
there will be some more details in lower levels.
Yeah, so I should really make it more clear. So yeah, each low-level FSM is specific for each scenario. So the 2 FSMs in the figure should have different trigger conditions, which is not shown. But in general, they may have different states. It just happens to have the same state in this particular picture. So the limitations of FSM-based behavior planning is first, state explosion for many and complex scenarios. The previous examples are very simple. Second is dealing with measurement noise and uncertainty of the environment. So you may use hyperparameters to deal with some noise, but only in specific limited situations. For example, the stop threshold, a hyperparameter. we saw before. And also incapable of dealing with unexpected and encountered scenarios. So the human designer must take into account every conceivable scenario. And humans are not always, limited. There are always maybe corner cases not covered by the current FSM. Then the behavior planner will be really confused. So reinforcement learning is a promising alternative, especially with deep reinforcement learning. You can be much more flexible and more handle corner cases in a more graceful manner. So before we go into the next part, any questions? So let's take a few minutes break because I want to finish the planning section today. So let's just take a 5-minute break. Yeah. Yeah. Okay, now we have finished the behavior planning. Let's go down one more level, down to the lowest level of planning, which is motion planning. So this is the vehicle control architecture, which shows the motion planning as a path generation and speed profile generation, which produces a trajectory to be tracked by the low-level control, longitudinal and lateral control, which further controls the actual steering, throttle, and braking actuators. So motion planning generates a feasible, which is smooth and collision-free trajectory from the current position to another forward position. So a trajectory is a path parameterized by time. So a path is just a geometrical concept, whereas a trajectory is a function of the path, a path as a function of time. So here it shows multiple possible trajectories, which are all feasible because they're collision-free, but you may choose one based on some optimization criteria. So motion planning is also called trajectory planning or local planning. So it generally includes two steps. One is path planning, one is speed profile generation. So path planning plans a path from point A to point B. So while avoiding the obstacles. Speed profile generation assigns a speed value to every point on a given path. So here's the fixed path, and you have an upper bound based on the speed limit, and then you may generate a speed profile along the path. So there's a method called variational planning, which combines both path planning and velocity planning to generate a trajectory in a single step. So here's an overview of the different path planning methods. So there's a geometric method which plans based on parametric curve. Could be a cubic spline, could be a Bezier curve, or some other curve. So it's complete. That is, if there exists an optimal path, it will find it. If there exists a path, it will find it, but it's not optimal. And variational method. So I'll just briefly mention it. So that's why I put a dotted square around it. So graph search methods. So you may have a lattice and plan based on the lattice, or you may have PRM plus Dijkstra. For incremental search methods, you may have RRT. So each of these methods has its pros and cons. So for the last column, anytime means that is the method, if the method is incremental and you can stop at any time and it'll return a suboptimal solution, then it's any time. So RRT and RRT star are any time. The others, yeah, and also this RG is any time. The others are not. You have to complete the whole procedure to find a solution. Time complexity are generally not so bad. So at most n log n, where n is the number of n is the input complexity. So the other attributes are completeness. That is, does it guarantee to find a solution if one exists? So most of these do not. Some of these are probabilistically complete, That is, with probability, very high probability, it's guaranteed to find a solution, but it's not an absolute 100% guarantee. So let's go into the details. First, the occupancy grid is the basis for planning, for all the planning methods. So occupancy grid is a discretized grid map encoding occupancy of static objects. So for example, all non-drivable surfaces are occupied, including trees, buildings, sidewalks, lawns, and so on, obtained with either LiDAR or camera. For example, with camera, you have the semantic segmentation we discussed before. So you may have two types of occupancy grids. One is binary encoding, where each grid box is encoded as either 0, free, or occupied. Or you may have probabilistic encoding, where here we have 94% probability of occupied and 12% probability of free. So 94% for this box. And then you may have a belief threshold to convert to binary encoding. For example, 50%. If the occupied probability is higher than 50%, you give it a occupied encoding. Otherwise, it's unoccupied, it's free. So given the occupancy grid, you can perform planning based on it. So one is the variational method. So this is by optimizing, optimize the trajectory by minimizing a functional, j with x plus delta x, which contains penalties for collision avoidance and robot dynamics. So for example, starting from this path, which has a collision with the obstacle, you gradually optimize the functional by, and optimization procedure will gradually, by reducing, minimizing this cost, it'll try to avoid the obstacle. And also robot dynamics, that is, the path should not be very discontinuous. It should be try to be smooth as possible to help the downstream controller to track the path. So this method can be slow and may not converge to a feasible solution. So I just give a very brief introduction on this slide. I won't discuss it further. So RRT, rapidly exploring random tree, is a very common method for path planning. So you insert some start location S in the tree, and while tree cannot connect to the goal, you sample a random point and find a point P in the tree that's closest to the random point, and add a branch between P and R. So another variant is to add a branch of predefined length from P in direction of R. So if new branch intersects obstacle, then you delete the new branch or shorten it. So so here's an example starting from the source. You want to get to the goal, G, and there are two obstacles in the middle. So you sample a random point. Suppose you sample the point 1. You may sample at some other position also. Suppose you sample point 1. Then you connect 1 with S, add a branch. And then you sample point 2, and connect 1 and 2. And then you sample points 3 and 4, and connect 3 and 4. And then you sample point 5. So point 5 is closest to point 4. However, the branch intersects with the obstacle. There's a collision. So you delete it. This branch doesn't work. you sample another point 6 and connect it with point 4. So, and there may be a shortcut path. So for any 2 points in the path, add a direct line unless the direct line intersect an obstacle. So that's just optimization. So in this example, it'll keep sampling in the open space until eventually it'll reach the goal position. So path smoothing is, so suppose you have found a path from the start position to the goal position, but it's a series of line segments. So if you're a robot or a car, you are trying to follow this path, you will have a very hard time because it involves some very sharp turns. So you smooth it to make it easier for the robot to follow. The smoothed path obtained by iteratively sampling points between nodes on the overall path, and then checking if 2 points could be connected to reduce the path length. So eventually you get a smoother green path. So here's the animation. You can watch the tree, the graph grows in a random manner. Eventually, it pretty much covers most of the free space, and then it'll reach the goal. So in this link, I think this link shows this example and the MATLAB code, and this is the actual So this robot is actually doing the RRT physically in the space. But in reality, you perform the RRT in the computer virtually, and when you have obtained a path, preferably a smooth path, then you let the robot follow it. So this YouTube link provides many animations. So you can see the gradual growth process of the RRT. So many points really do not end up anywhere, but eventually there has a high chance of reaching the goal, although not guaranteed.
I have a quick question here.
Sure.
Why you computing this RRT? I think then we need to make an assumption that all the other objects, or maybe in this case, cars, that they having a static, like their trajectory is static and their speed is also static, right?
Yes.
But would that really work in a dynamic environment though? Like thinking about real life scenario now on the road? Whereby you start with an assumption like, okay, but then the person that is maybe on the left and in front of you can also like increase their speed and also their trajectory.
Yes. So these the methods shown in the table they generally assume static obstacles. So if you have dynamic obstacles, then things get more difficult. So you need a behavior prediction step for predicting the possible paths of the other traffic participants, and based on that, you need to perform the behavior level planning, which must be aware of the dynamic obstacles. Whereas motion planning is the lowest level of planning. In the for the dynamic obstacles, I think that the motion planner, for example, in here, when you are planning a trajectory, you should be aware of the other obstacles around you. So that's why you need to plan a trajectory, not just a path. So the path may be safe or unsafe depending on your speed and other vehicle speed. So that's why that when you're doing the planning, you need to consider the other traffic participants also. In terms of the algorithm, I think in the lecture I only show the assuming all the obstacles are static, but for the dynamic obstacles, you do need to enhance the algorithms.
Okay, thank you.
Yeah, so in fact, this is a major difficulty in planning. That is how to deal with unpredictable and outside dynamic obstacles. So that's why reinforcement learning has been proposed as a solution to planning instead of the current methods. The current methods are so-called modular architecture. That is, you have perception module, a behavior prediction module, a planning module, and then in planning you have 3 separate modules: high level, low level, mid level planning. So this is a very modular architecture. And in the higher level, you need to make predictions on the other dynamic objects. And based on the predictions as input, the low level can plan based on that. Whereas for reinforcement learning, you can map end to end from your surrounding environment to your action, whereas let the neural network take care of all the complexities. Neural network will perform the prediction of the other traffic participants and take into account the other dynamic objects in the decision process automatically. So that's one benefit of the end-to-end learning approach. That is to handle the complexity not by human design, human expert, but by learning, training a deep neural network. So that's RRT. So probabilistic roadmap works by first constructing a map. So the process is so while the number of points in the roadmap is lower than the threshold, you sample a random point, and if the new point is not in collision, connect new point to all other points in the roadmap with lines as long as they do not intersect obstacles. And after you have constructed the map, that is all the lines, you do the path finding at the next step. So you connect start location to nearest point in roadmap so that the connecting line does not intersect the obstacle, and you connect the goal location to nearest point in roadmap such that connecting line does not intersect with the obstacle. And then you'll find a path between start and goal traversing the roadmap with algorithms such as a star or Dijkstra's algorithm. So here, the granularity is at a much finer granularity. So A star and Dijkstra can be used for low-level motion planning, say from say just between two locations with a few meters distance with obstacles in between, or it can be used for high-level mission planning, say between your home and office. So they're both applicable. So compared to the RRT, the PRM is a two-step process. You first construct a roadmap, that is all the line segments, and then you plan based on A star or Dijkstra on the roadmap. Whereas RRT essentially searches, grows the tree until it reaches the goal. So these two methods, yeah, the difference are shown here. So with RRT, each time a new start and goal locations are given, an entirely new graph must be generated, which may be very inefficient. Whereas PRM builds a roadmap first for traveling through a region, and then relies on A star or Dijkstra's algorithm to find the shortest path from start to goal traversing the roadmap. So the roadmap is reused each time new start goal locations are given. So after you have constructed the roadmap, so you can choose any point as start, any point as goal, and the roadmap stays constant. You just need to find a different path through the roadmap. So in this sense, PRM is more flexible. So there are many variants of RRT and PRM. So RRT star, and many papers have been written about them. So they are probabilistically complete. So which means that if a path exists, it will be found in finite time. But in the worst case, solution can be very long, even longer than exhaustive search. So imagine that you're just a very unlucky algorithm, and all your random points happen to miss your goal, which is not likely but possible. So that's why in the worst case, it may take you infinite time to find the goal, or you may never find the goal. But on average, it's not likely that the worst case will happen, and the algorithm will finish. And also there's no guarantee on solution quality. It may not find the shortest path. So with PRM, the A star and Dijkstra's algorithm is guaranteed to find the shortest path for the given roadmap. But the roadmap itself may not be optimal because it's generated randomly. So, and also you may often need post-processing, for example, smoothing, to reduce the curvature and make it easier to track. So here's a simple quiz. Which statement is true for RRT and PRM? So answer is B. Both algorithms can be used for high dimensional spaces. So especially for robotic motion planning, which may be very high dimensional. So for a robot with many joints, you may have hundreds of dimensions with rotational and translational joints. Whereas for mobile robot, for vehicles, it's relatively low dimensional. For ground robot, it's 3 dimensions, and for aero robot, it's 6 dimensions. But for generally more higher dimensional planning problems, RRT and PRM can be very effective. The others are false. So both algorithms will produce the shortest path. There are no guaranteed. These are probabilistic algorithms. PRM always results in a better path than RRT, not true, and not true vice versa. Time for computation is consistent and predictable, also not true because it's probabilistic. So now the other method is a parametric curve-based planning. So we have been discussing RT, PRM, A star, Dijkstra. So all of these methods they represent a path as a sequence of points. So on a grid map. So it's a so-called non-parametric path. Whereas for parametric path, it's a smooth parametric curve that satisfies boundary conditions at two endpoints with constraints on curvature and optimizes an objective function. So for example, you have a start point with x0, y0 is your position, and theta is your heading angle. So for example, your vehicle's heading angle, remember the bicycle model? And kappa is the curvature at this point. So curvature is just 1 over the radius of rotation. So suppose you're given the start and end points, each one is a tuple of these 4 numbers, and you impose the upper bound on the curvature along the path to help satisfy kinematic and dynamic constraints and improve rider comfort. So obviously a smoother path is easier to track with either kinematic controller or dynamic controller. And also it's more comfortable to the rider. So we'll explain 2 examples. One is a quintic spline, and the other is polynomial spiral. So quintic spline, the path is modeled as a 5th order polynomials with closed form solutions for boundary conditions. So here's an example from the starting point to the end point. So this is the solution. So you have a variable u. If u is 0, it is the start point, and u is 1, it is the end point. And you need to solve for the parameters alpha and beta based on the boundary conditions. So you can solve for this for these parameters in closed form for the given start and end points. This is the pro. The con is that the curvature function and its derivatives may be discontinuous. So you cannot easily control the curvature. So polynomial spirals is another method. So you define the curvature as a polynomial function. Here, kappa s could be cubic or higher. So it's smooth and never discontinuous. So you can constrain a few points on the path to constrain the entire curve in terms of the maximum curvature. So and then you model the paths as first you have a theta defined as this function as the integral of the curvature with regard to the s variable, and then you get the x and y as integral of cosine theta and sine theta. So theta is the heading direction of your vehicle. So the pro is that the curvature function is smooth. So you can impose the upper bound on the curvature along the path. The con is that now the path does not have a closed forms equation as a solution. So this integral of cosine theta s prime ds prime and sine theta s prime ds prime, because the theta itself is a complex function, it does not have a closed form solution. So you must use numeric methods. It's called a Fresnel integral. It must be computed with a numeric integration rule using Simpson's rule with pretty high computation overhead. So Simpson's rule computes the integral of a function with this formula. So where n is the number of segments. So for example, you need to compute the integral of this function, the smooth function f. So you divide the segment between x0 and x1 into n segments. So n is equals 2 in the figure. So now you're approximating the integral. So this is your true function, and your true integral is the area of this area, whereas your approximation is is this function, smooth shape. So this is a way of taking a few sample points in the interval and compute the integral based on the smooth interpolation between these sampled points. So another simpler method is the simply take the sample points and just take the left value and add up the areas underneath. But this Simpson's rule is more accurate. But however, the drawback is that this method of performing integration is very computation intensive with high overhead. So what's the optimization function for the say suppose you model the curvature as a cubic spiral, so you may minimize the bending energy as the integral of squared curvature along the path in order to distribute the curvature evenly along the spiral. So you want to minimize this function, whereas remember the curvature is defined as here. So kappa s is a cubic polynomial, and you are trying to minimize the kappa squared integrated over the entire path. So by minimizing this, you try to smooth out the curve so that the curvature is evenly distributed. So subject to constraints, first is the endpoint constraints at the two endpoints, start and end positions, and curvature constraints for two intermediate points. So here you pick 2 points in the middle and impose a kappa max for the curvature, and then the entire path will satisfy the kappa max because of the smoothness of the path. So there are proofs behind these statements, but I'm just saying this without any proof. So here's an example of a cuntic spline versus a cubic spiral. So x, y position. So they look pretty similar, at least for this simple case. Yeah. So another method is conformal lattice planning. That is to plan the collision-free path to go exploit road structure. That is why it's called conformal lattice planning. So you're conforming to the road structure. The road may bend, so you need to bend your paths and generate a set of lattice paths laterally offset from a goal point along the road. So the goal point is dynamically calculated based on speed and other factors. So longer look-ahead horizon improves ability of collision avoidance, but increases computation time. So other endpoints are sampled with lateral offsets from goal according to vehicle heading. So here's the example. Suppose the vehicle, eagle vehicle is at this position, and you look at horizon is this far ahead. So you need to plan a path in the look ahead horizon. So suppose this is your goal point. That is this point along the path. So obviously you have a straight line path, but you draw some additional paths to the neighboring points, other endpoints, with a lateral offset from the goal. And for each endpoint, including the goal point, you solve the optimization problem to get a spiral, and then use numerical integration, for example, trapezoidal rule, to generate points along the paths. So the reason that you sample the many endpoints is for avoiding collision. So you perform collision checking for each point along each path. For example, here you have maybe a vehicle that's broken down on the road, the red box. And your eagle vehicle is at this position. You need to plan a path around it. So suppose your goal point is here. You want to go from here to here. So the straight line path has a collision. So you have the additional endpoints for each one. You perform collision checking, and turns out the middle few red paths all have collisions because your eagle vehicle also is a box. So even though this red line seems there's no collision, but actually there is a collision because your eagle vehicle is not a dot, it's also another box. So along the collision-free paths, select one based on a custom objective function. For example, here we select the blue path, this guy. So it avoids the obstacles while it prefers to be close to the center of the road. The other paths are also feasible, but they deviate too much from the center of the road. So from a safety perspective, it's better to stay close to the center of the road. So and penalizing paths that come too close to the obstacle. So that's a conformal lattice planning. So and then you repeat this process for each planning period in the receding horizon manner, just like MPC. So after you have done the planning, you move ahead and then you replan, and gradually. So suppose that initially from the picture here, the waypoint is here. So so your waypoint is initially here. So you plan a path. the path is going to here, right? But at some point you replan. At this point, and at some point you replan, and eventually the blue path is the final path that the vehicle actually traverses. So the full path will converge to the center of the road after passing the obstacle. So after we have generated the path, the next step is to generate a speed profile along the path. So from the behavior planner, the high-level planner, it provides reference speed to local planner. So could be the current road speed limit, 55. Could be the current maneuver, could be stopping due to a stop sign or red light, or following a lead vehicle. So that's a reference speed. And you can compute the time to collision, TTC, by differences in the eagle vehicle speed and the lead vehicle speed, divided by the distance, S. So that's one constraint on your speed based on the traffic rules and the lead vehicle. The other constraint could be based on the curvature. So the velocity is upper bounded by the lateral acceleration and the curvature. So this formula can be derived, but I won't show the derivation. So intuitively, the higher the curvature, the smaller the maximum speed. So it makes sense intuitively, right? So if your road is very curvy with a very sharp turn, you shouldn't drive too fast. So that's another bound on your speed. And the final reference speed is selected as the minimum of all the upper bounds based on the curvature, based on the traffic rules, time to collision, and so on. So here's an example of speed profile. X is the position, X dot is the speed, X double dot is the acceleration, X triple dot is the jerk. So the jerk really it's used in the automotive context as a measure of comfort. So if a trajectory has a very high jerk, the passenger, the rider wouldn't feel very comfortable. So so here's two examples. One is aggressive jerk. One is a comfortable jerk. So here, the acceleration initially is very large. Acceleration increases from 0 to 2 and stays at a constant 2 and drops from 2 to 0. So the velocity increases linearly based on time because it's constant acceleration for most of the paths. The jerk is very high in the beginning. Jerk is acceleration derivative with respect to time. So initially it has very high jerk, and at the end you have another high jerk. Whereas in the other paths, you have a gradual acceleration and gradual deceleration. So the speed profile is this. It's smoother, whereas the jerk is also very smooth. Only a little jerk in the middle. So obviously, this choice is a much more comfortable ride for the rider. Here's an example of a linear ramp profile with a constant acceleration to reach a reference speed. Here's an example of a trapezoidal profile with a constant deceleration. For example, this could be used for stopping at a red light. So for the linear ramp profile, you can compute the acceleration with this formula. Suppose your path length is s, and initial final speeds are v0 and vf. So consider a robot with starting speed v0 and constant acceleration a. So after time t reaches a speed of v0 plus at equals vt, and travels the distance of this formula, which is the average speed v0 plus vt divided by 2 times the time, which is vt minus v0 divided by a. And you get this formula. So that's where this acceleration comes from. For a linear ramp profile. So you may clamp acceleration a to improve rider comfort by clamp, imposing upper bound. So for each path segment, compute the speed using accumulated path arc length RSI up to that point to generate the speed profile with this formula, which is derived from this guy. So at every segment, you compute the VF based on the acceleration A and the speed at the start point of the segment. And so you do this for every segment to get a series of speeds along the path. So in every segment, you have the linear ramp profile. But over the entire path, you may not have a linear profile. For the trapezoidal rule profile, you do the calculation this way. So for a given total path length s, initial final speeds v0, vf, and transit speed vt, for the first segment, this segment, you compute the path arc length as this, as derived before. Then you compute the speed profile based on this formula. Vf equals, you just solve for the vt from this formula. So for the second segment, it's a constant speed segment. So for the third segment, the speed drops down to 0. You compute the arc length, and then solve for the final speed based on this formula. So this is just computing the speed profile, computing this curve based on the s arc length information for a trapezoidal profile and for the linear profile for the previous slide. So this slide is based on the Coursera MOOC on self-driving cars, but that particular lecture has a typo, yeah, which I have corrected. Any questions on this segment, motion planning?
Yes, I can have one maybe.
Oh, sure.
I remember when we were playing with robots playing soccer, football. The goal was moving all the time, typically the ball or something, and the obstacles, which is the opponents and so on, is also moving all the time. Have you seen any methods for dealing with this kind of dynamic environment? I guess it's the same in the traffic because the vehicles are moving all the time as well.
Yeah. Indeed, I mentioned this a little before. For dynamic objects around you, you need to take into account the dynamic objects during your planning, for your local motion planning. So it's very challenging and it's not covered in the course. But these are basically improvements, enhancements over the basic methods.
So if you have a kind of quick method, you can run this very often or something to try, at least as a try.
Yeah. So for example, MPC could be used for trajectory planning. So model predictive control we discussed before for tracking a path, a trajectory, but also you may use it for the trajectory planning, and it's also called receiving horizon control. So in this context, you can do receiving horizon planning. That is, you plan for a horizon, move forward, and replan based on the current situation. Yeah, I think it's actually a well-known term.
Yeah. And I know Sven at our department also made a planning, some kind of route planning with circles. So you kind of put circles in front of you where it was possible to go with the robot. So
you mean to take into account the robot's size?
Yeah, the size and the obstacle and how they can turn and so on. So I will send you the article, my only one, I think, at TV. So.
Oh, yeah. So that's that is for collision avoidance and collision checking. You need to take into account geometry of the objects. So you can either enlarge every other obstacle by the size of the robot, and then your robot can be viewed as a single dot, right? Mm-hmm. Or you can treat your robot as a box with a size, and then perform collision checking. I think I want to finish the rest of the lecture. So let's finish maybe half an hour late, because it's recorded anyway. So any objections? Okay, so let's do it. Let's talk about RSS, responsibility sensitive safety. Absolute safety is impossible. For example, in the scenario below, the AV, the yellow car in the center lane, can do nothing to ensure absolute safety. If the red car on the right swerves into the AV, the collision cannot be prevented. So to avoid this scenario, should the AV never drive in the center lane, or should it never leave the garage? So avoiding collisions at all costs leads to a useless system. That is, your AV should not have the goal of being absolutely safe, because that means your AV will never leave the garage. There are hard traffic rules that sets a limit on vehicle operation. For example, come to a complete stop at red lights. Do not cross a double yellow line. Obey posted speed limits. Yield to other road users when signaled. So these are all rules that can be programmed into the AV. So these are easy cases, but there are difficult cases that are implicit traffic rules. That's a set of general principles applied by the human driver. They are flexible and culturally dependent. Keep a safe distance from the car in front of you, or drive cautiously under limited visibility. Don't drive slowly in the fast lane. Don't cut off other drivers. So how to formalize and program these rules into the AV? And these rules are maybe different in different countries. So if you are driving in a large city in India versus driving in a small town like Umea, the rules, implicit rules, may be different. So RSS formalizes human notions of safe driving into a verifiable model with logically provable rules. It defines appropriate responses and ensures that only safe decisions are made by the AV, and clearly assigns blame responsibility in case of accidents. So the goal is that AV should never be responsible for accidents, meaning that it should never cause accidents, and it should properly respond to mistakes of other drivers. So it's a mathematical interpretable model formalizing the implicit rules, common senses. What is a dangerous situation? What is the proper response to a dangerous situation? And who is responsible for an accident? So let's watch this short video.
Everyone agrees that autonomous vehicles are the future of mobility. But how can we be assured of their safety? Although we don't consciously think about it, humans follow a few basic principles to help us drive safely. For example, always maintain a sufficient distance from the vehicle ahead of you, or the right-of-way is given and not taken. However, these principles are subjective and open to interpretation. To provide true safety assurance for autonomous vehicle decision-making, we must first clearly define those principles. Only then will we be able to program an autonomous vehicle that will be smart enough to negotiate the road alongside unpredictable human drivers. In order to formalize human common sense, Mobileye has developed the responsibility-sensitive safety model. RSS is an open and transparent model that uses mathematical formulas for safe decision-making by defining what constitutes a dangerous situation, what caused it, and the proper response to the dangerous situation. By doing so, we can ensure that the autonomous vehicle will not initiate a dangerous situation, and also ensure that it responds appropriately when a dangerous situation is forced upon it by others. For example, while merging into traffic, the autonomous vehicles will cut in only with a minimal safe distance as defined by RSS. RSS builds upon these simple definitions of a dangerous situation by incorporating more complicated scenarios, such as junctions, limited sensing scenarios, and even unstructured roads. This allows us to gain full coverage of all possible scenarios in a multi-agent environment and clarify responsibility for collisions involving automated vehicles in the real world. These are just a few examples of how RSS is designed to mimic human judgment using mathematical definitions. At Mobileye, we believe that the challenge of providing verifiable safety assurance of automated vehicles is one the entire ecosystem must solve together. Therefore, we invite industry players and regulators to engage with RSS as a starting point for finding a true safety guarantee for autonomous vehicles. Join us in our journey to make safe autonomous driving a reality. Mobileye.
So there are 5 rules of RSS. First, do not hit the car in front. Keep a safe longitudinal distance. So here's a example figure. So this Eagle vehicle should keep a safe distance so that it's possible to brake in time to avoid collision. Do not cut in recklessly. Keep a safe lateral distance. Right of way is given, not taken, and be careful in areas with limited visibility. And if you can avoid a crash without causing another, you must. So RSS defines a safe distance. For example, longitudinal distance. And if a situation is dangerous, if it's non-safe longitudinally, and blame time is the first moment in which the situation becomes dangerous. Proper response is if the longitudinal distance becomes non-safe, then brake longitudinally. That's the proper response to the dangerous situation. Responsibility. So we prove that a collision can only occur if one of the agents did not respond properly. So the responsibility is on the agents that did not respond properly. So by this, you can assign responsibility so that AV is allowed to have accidents as long as it's not responsible for it. So here's an example of a non-safe lateral maneuver. So the red vehicle is turning in the turning left, so it's cutting into the yellow's lane. At this point, the red is to blame, and its proper response is to brake laterally. So in this context, brake laterally means that brake while steering to the right direction. So after the proper response, the red vehicle is traveling in its own lane. So this is just a few concrete examples of the concepts in the previous slide: blame time, proper response. So here's another example. So these two vehicles are traveling in the same direction, and the blame time here, the yellow is driving too fast and getting too close to the red vehicle. So the proper response by the yellow vehicle is to brake and to increase the distance from the red vehicle. So that's an example of non-safe longitudinal maneuver and the proper response to it. Here's a situation of hit from behind. So if two cars are traveling in the same direction, the yellow is hit from behind by the red. Then yellow is not responsible for the accident. A side hit. So if the red is traveling in its own lane and the yellow hits it from the side, then red is not responsible for the accident. So the AV, the blue car, should keep safe longitudinal and lateral distance from the other cars. So then if the front car slams on the brakes, how much longitudinal distance does it need to avoid a rear end collision? And if the left or right car suddenly swerves, then how much lateral distance does it need to avoid a side collision? So these are the questions RSS wants to formalize with mathematical formulas. So let's focus on this rule, safe longitudinal distance. So consider two cars traveling in the same direction, front car CF and the rear car CR. In order to ensure that CR never hits CF from behind, it's the responsibility of CF to keep a safe longitudinal distance dmin from CF, which should be large enough so that CR will not hit CF, expressed in this formula. So the worst case situation is that CF will suddenly break hard. Then it'll take CR some response time, rho, including the sensing and reaction delay, to figure this out and to start breaking as well. And then both cars will decelerate. So assuming the known parameters of beta max, the maximum deceleration rate due to braking for the front car, beta min, the minimum deceleration rate for the rear car, CR, and alpha max, the maximum acceleration rate for CR. You can derive d min as this formula. So the proof is on this page. So I drew 3 figures. First is the position versus time, longitudinal position. Second, the velocity versus time. Third, the acceleration versus time. So the red line indicates the position, velocity, acceleration for the front car. The black line indicates the values for the rear car. So the initial distance between the front and the rear is d0, assuming the beta min less than equal to beta max. That is the front car brakes harder than the rear car. So the distance will decrease monotonically with time, like this. So to avoid collision, the minimum initial distance d min can be obtained by assuming that both cars will stop, come to a full stop at some time tc at this point, with distance d equals 0. So that's the worst case. So at time 0, front car and rear car have initial speeds vf and vr respectively. So velocity here. And in the time interval 0 to rho, so remember rho is the reaction time, response time, including sensing and compute reaction delay. So in this time interval, the rear car has not realized that the front car is braking. So it's still accelerating or driving at constant speed. The worst case is that the front car applies the brake with constant deceleration beta max, and the rear car accelerates with constant acceleration alpha max, because the rear car is not aware that the front car is braking. Now at time rho, the rear car realizes that the front car is braking. So to avoid collision, it should start to brake. At this point, the rear car has reached a speed of VR, the initial speed, plus rho times alpha max, and travels a distance of the average speed, VR plus a half rho alpha max, times the time interval rho. So after time rho, the rear car starts braking with constant deceleration beta min. So travels a distance of v squared over 2 beta min. So the numerator is the VR plus beta alpha max. That is the speed at this point at time rho. So at a time interval 0, at a time interval 0 to rho and rho to tc. So in the entire time interval, the rear car travels a distance of vf squared over 2 beta max, because assuming that it comes to a full stop at time tc. So the average speed is vf over 2 times time to stop. I think I have another typo here. BF. I think it's rho. So finally, at time tc, both cars come to a full stop with distance d equals 0. So that's the worst case. So the minimum initial distance, d min, is the distance traveled by the rear car before full stop minus the distance traveled by the front car before the full stop. So this part is the front car's distance, travel distance from 0 to rho, and this part is the front car's travel distance from rho to tc. Oh, sorry. It is 0. So it's the entire, yeah. So this is the front car's distance. This is this car's distance. And this is the rear car's travel distance. Did I make a mistake here? Let's see. Rear car applies brake. Rear car travels. Front car travels. BF. Sorry. Okay, sorry for the typo. This is the front car. That's why. Yeah. Okay. So so for the rear car, it has 2 stages. From 0 to rho, that's when it travels this distance. So it's accelerating at alpha max because it's not aware that the front car is braking. The next stage is here. So that's this distance. That's when it realizes that the front car is braking. So it also brakes at beta min. So the front car travels the distance of this. So front car is braking all the way from 0 to tc with beta max. So this is the front car's travel distance. So, and then the rear car, so suppose both cars come to a full stop at this point. Then the rear car has traveled a distance of this, and front car has traveled the distance of this. So their difference is the d min that we want. So assuming all the parameters are there, we know all these parameters, and we know that at this point, both cars come to a full stop and they're barely touching. So that's the worst case situation, and we compute the d min based on that. Any questions? So this RSS formula allows you to formally define the desired balance of safety and efficiency of AVs on the road. For example, d min could be larger if you assume a large deceleration rate, beta max, for the front car, or a larger acceleration rate, alpha max, or smaller deceleration rate, beta min, for the rear car. So the AV will drive more conservatively, keeping a longer distance from the front car, so resulting in lower efficiency, and also vice versa. So now you may ask, where do you get these parameters? Beta min, alpha max, beta max. So these parameters should be determined by regulatory authorities working with the car makers. For example, the National Highway Traffic Safety Administration in the United States. So the point is that when these parameters are known, when it's an industry standard, that's why RSS is proposed by Intel Mobileye, but it's being standardized by the automotive industry. Because if only one company respects these RSS rules, it's not useful. Only when everybody respects these rules, then it's useful. So when everybody agrees on these parameters, acceleration, deceleration rates, then if everybody implements these rules by keeping a minimum distance, you can prove that the rear-end collisions will never occur.
Excuse me?
Yes?
Does it mean that actually the beta parameters are not decided, I mean, completely decided by the physical characteristics of the vehicle, but just administrative parameters?
So these are vehicles' intrinsic parameters. So for example, beta max is a maximum deceleration rate. So if your car has a really good brake, it can decelerate from 100 kilometers per hour to 0 in 1 second. Then your rear car will have a really hard time not to collide with you, right? So similarly, if your car has a really bad brake, then it's likely that you collide with the front vehicle. So the point in having these constraints or parameters defined as industry by the entire industry is that everybody has a measure of other people's behavior, so that you can apply these formulas, these rules, to define a safe distance so that you can keep the safe distance during operation. If you do not have bound on these parameters, then, I mean, say you're following a front car at 100 kilometers per hour. So how far should you keep from the front car, right?
I mean, it's misunderstanding because I know that physical characteristics of the vehicle or engine and so on decides how fast the vehicle can stop. But the question was regarding because you mentioned that they have decided, like regulators needs to decide beta parameters, but how is this? Also, like, is this just some kind of how formula for beta should be should look like, and then every manufacturer should use it for their own vehicles? Or I'm not really sure. I don't understand how, like, where regulator goes in and what he decides regarding beta.
Oh, so this should be an industry standard that's agreed upon by the vehicle manufacturer. So that, for example, the Alpha Max should be respected by, say, Volvo. So Volvo should promise to the certification authority that Volvo cars will never accelerate at a higher rate than Alpha Max. So that's an agreement with the vehicle manufacturer, with the OEM, as a contract. Similarly for beta. So if you have these agreements, industry-wide agreements, then
I mean, for alpha it's more clear because you can limit the acceleration, but for the what's called the acceleration, it's not. You can't really just by the rules increase or decrease stopping distance. because it's dependent on the vehicle characteristics.
Oh yeah, yeah. So in terms of the beta, I think it's really yeah, I guess if you force a company to degrade their brakes, not to brake too fast, maybe it's not a good idea, right?
No. But it's okay. It's okay. Then we don't need to go into details. But it's like I thought maybe it's that they commonly agree how data formula looks like, and then it will be applied for each and every vehicle. So like this value is standardized, so everybody is calculating correct way in the same way, not correct.
Yeah, yeah. So the point is to have an industry standard on these parameters. Exactly how do they enforce them? I have no idea, because the standard is in progress. It's not yet a standard. So RSS is still mostly an Intel thing. Intel is pushing it very hard, but it's being standardized, but it's yet to be made a standard. So we don't know exactly how these parameters will be enforced with OEMs. Yeah, it's a work in progress.
Okay, yeah, thank you.
So the moment the distance between two cars is less than d min, the AV will perform the proper response. So after response row, apply braking of at least the beta min until a safe distance is restored, or until the vehicle comes to a complete stop. So RSS can be a proactive safety mechanism that improves automatic emergency braking. So it could be called automatic preventive braking. It determines the moment when a vehicle enters a dangerous situation, then it uses comfortable subtle braking beta min to help return the vehicle to a safe position without waiting for an imminent collision to engage maximum braking force. So the preventive approach would provide a stopping distance buffer that could prevent a chain reaction of braking and swerving should an emergency stop occur. RSS is not intended for emergency collision avoidance. It's more intended for collision prevention during normal driving situations. So other RSS rules, I'll just briefly describe them here. So one is a safe lateral distance. So it enables AVs to be aware that when their lateral safety may be compromised by unsafe drivers turning into their lanes. So there's a similar formula for that. Rule 3 is right of way is given, not taken. So on well-marked roads, right of way is clear. Lane lines, signs, and traffic lights establish priorities for routes as they intersect one another. But there are other times when the right of way is less clear. So human drivers must negotiate with one another. So there's RSS rules for that. Rule 4 is be cautious in areas with limited visibility. The drivers must proceed cautiously, especially as they approach crosswalks or pass cars parked along the street, because a child may jump out from these cars. Rule 5 is if the vehicle can avoid a crash without causing another one, it must. So for example, if boxes fall off the front car and the next lane is free, the following car can take evasive action to avoid the accident. So I won't go into the details of these other rules. So RSS is open source C++ library. It has been integrated into Baidu's Apollo's planner module and the driving simulator Kala. So Apollo is a very widely used open source self-driving car stack. So here's the Apollo's planner. So So the yellow boxes are the RSS modules. So it has a decider. So given upload road environment, it issues the check result of whether, so for longitudinal direction, it issues acceleration restriction based on RSS rows. So Carla, the driving simulator, so it uses the RSS library to evaluate if a driving situation is safe or unsafe. So it composed of an ego vehicle and another traffic participant, a leading vehicle. So the sensor evaluates longitudinal and lateral conflicts, but does not yet cover intersection conflicts in the simulator. So here's the green indicates all safe, and the red indicates dangerous situations that require to a countermeasure according to RSS. So here, the green is the distance from this vehicle to this vehicle. So it's pretty far, whereas the red is from here to here. So it's pretty close. So based on RSS, a rear vehicle should brake. So here's the video. So as the car, the ego vehicle drives, so yellow is unsafe, green is safe. So it turns into green as the distance between cars enlarges. So here, so it handles both longitudinal and lateral conditions. So whenever it turns red, the rear car should brake. So in a sense, RSS really, if you read the RSS rules, it's like reading a driver's manual when you're taking the driver's test, right? So it really formalizes the common sense in driving in your driver's manual, and because they formalize it, you can implement these with the code and encode this behavior into the AV's behavior. So there's another interesting initiative by NVIDIA called the safety force field. It's a robust driving policy that analyzes and predicts the vehicle's environment, determines a set of acceptable actions to protect the vehicle as well as others on the road. The actions won't create, escalate, or contribute to an unsafe situation and include the measures necessary to mitigate harmful scenarios. So it's criticized by Mobileye to be a close replica of RSS. So if you watch the video, you can see they really look very similar.
We all would like a vehicle that monitors the surroundings and shields us from collisions. The safety force field is a practical realization of that. It's not possible to guarantee safety regardless of what other actors in traffic do, but it is possible to guarantee that we do not contribute to an unsafe situation. If all actors in traffic had that sort of guarantee, then no unsafe situations or collisions would occur. The safety force field takes the vehicle's understanding of the surroundings and determines a set of acceptable actions. To do this, it uses a constructive computation to consider which actions are helpful in maintaining obstacle collision safety. The acceptable actions never create or escalate an unsafe situation, and this computation can be combined with any software for autonomous driving as a layer in the motion planning that monitors and protects against unacceptable actions. The safety force field follows from one core principle as opposed to a large set of rules and exceptions. So the beauty of the safety force field or a provable planner of this type is that the guarantees that it provides have been mathematically proven, and it seamlessly can handle highway driving, cluttered urban scenarios, and even unstructured parking lot type of driving. It also separates cleanly obstacle avoidance safety from a long tail of rules of the road. The real world is a very complex place, and we have to understand that ideally it would be there as a sort of veto power on anything unsafe that would occur. And the motion planning and other things that would operate on top, or even a human driver, if you had this underneath, would do the normal everyday driving. And if you did brush up against an unsafe situation, then it would push you in the right direction and keep you safe. It considers longitudinal and lateral constraints together, and the constraints can also be visualized in a very direct way. It's a beautiful thing that we have Drive Sim to our disposal at NVIDIA, where it's in the nature of something like the safety force field that the situations we want to test it in are inherently very dangerous, and we could do that in Drive Sim without putting anybody in harm's way.
So in fact, Mobileye's CEO has some very harsh words to say to NVIDIA. So in this blog, innovation requires originality. The CEO says, despite uncanny similarities, NVIDIA's SSF fails to match Mobileye's RSS, which is the leading AV safety model, and so on. So then he goes into details and lists a table and a huge PDF file to list the similarities between these two. So essentially, he says NVIDIA is plagiarizing Mobileye. I mean, it makes sense, right? If it's industry standard, whoever makes the standard gains the advantage over the others. But so point by point, it looks very similar. So summary, RSS formalizes what is dangerous, what is the proper response to danger, and who's responsible for accidents. So AV is allowed to have accidents as long as it did not cause it. So soundness says it complies with the common sense of human judgment, and usefulness says we give 100% guarantee to never cause accidents, not to be never involved in accidents, and always properly respond to dangerous situations. Okay, so that finishes the lecture on planning. So any questions?
I have regarding this allowed accidents.
Yeah.
I wanted to ask, actually, that was the question I wanted to ask since you mentioned it first time. What do you mean, or what is meant by this, that is that vehicles is allowed? If it's not responsible, it is allowed to have accident. It's like,
I mean, it's the other vehicle's fault.
Yeah, I understand, but why should be? I mean, I don't see that. Is this like that a vehicle won't, because it will try to avoid accident anyhow. But if it's not avoidable, is it like then it's allowed so that it doesn't get like stuck in the program, because this is not predictable situation. Like that's why it's permissible.
So let's look at this particular rule. So if a rear vehicle keeps a demand from the front vehicle, and all these parameters are standardized, everybody knows these parameters, then it'll never collide with the front vehicle. So, I mean, without these formal rules, how far you need to keep the distance from the front vehicle is not clear. Different drivers have different behavior, and it's hard to encode the behavior into a AV. So do you want to be very conservative, like an 80-year-old lady, or do you want to be, you know, a little aggressive, like an 18-year-old youngster? So it's hard to say. But with these rules, you can be very formal. And in case of accidents in the court of law, you can use your drive logs to demonstrate that you have respected RSS rules. Therefore, any accidents is not due to the fault of the AV. So I think that's very useful for assigning blame.
Yes, but I don't see really the reason why we have the rule that it's allowed to have an accident. It's like where that rule fits.
By allowing, I mean for the slide I showed before, in this situation, the AV, the yellow car, will have no way of avoiding accidents if some other car just swerves into it and has no way to turn. So that's why it's allowed to be involved in accidents. I mean, there are rules in RSS. For example, Rule 5. So if the vehicle can avoid a crash without causing another one, it must. So it does its best to avoid crashes, but it's only involved in accidents when some other car does something really bad and it's not its fault.
What I mean is like, this is like, you can't rule out accidents. So it's like, what I mean, we know that you can't avoid all the accidents if somebody else is somebody else's mistake. But I mean, if you say it's not allowed, it's no use of it. It's like this allowance. I don't see any purpose for this, because it's like you just can't influence it.
Yeah, maybe it's just the wording to be allowed in an accident. I mean, yeah, so it tries to avoid at its best effort, and when it fails to avoid an accident, is in a court of law, it wouldn't be held responsible. I think that's very important from a legal perspective for the AV vendors. Otherwise, you know, it's really hard to say who's at fault if AV is involved in an accident.
Yes, but this is, as I understand, this is like rules that are used for the decision making, and I don't see any usefulness of this rule in the decision making for those autonomous vehicles.
Oh, the decision making is it's very concrete. Say in the Carla video, whenever this line here turns red, it should brake based on RSS rules.
Yes, I understand, but this particular rule that accident is allowed, I don't see where it fits in the decision making, automatic decision making. Well, because I don't see any useful. Why is it? Because this is formal rule that is used for the implementing or developing systems that will make automatic decisions. But I don't see where this rule fits in.
I see your point. So I think it fits in the speed profile generation. So yeah, I think I should add something here. So for example, this ego vehicle speed can be limited by several upper bounds. So one is the one I shown here due to curvature. The other is due to the current stop sign or some other traffic lights and so on. Another is the time to collision. So this can be based on RSS. So this is a very concrete application of RSS. When you are doing this speed profile generation, use RSS to decide the upper bound on the speed and acceleration. Yeah.
Yes, but it's still, we don't need to waste some more time, but I still don't, I just want to say it. I still don't see even here this rule that it's allowed accident, how it influenced this model. But it's okay, we don't need to take any more time.
Yeah, so maybe there's some misunderstanding, but if you want, you can try to formalize your argument a little bit more and send me an email.
Okay, I'll
yeah,
do it.
Sure. Okay.
Okay, thank you.
Sure. Any other questions?
Just a comment. I guess this is also based that the sensors had a good view of what's happening. For instance, the red light, if they don't see the red light or things, or the vehicle in front, or
yeah. So RSS is a planning module. So in the Apollo stack is part of the planner, kind of like a safety check for the planner. So it's another issue. Perception is up here. So it's a different issue. Yeah.
But you don't plan for kind of misunderstandings in a safety way or so.
Yeah, if the planning module has a fault and you didn't see the stop sign, then it's the planning module's fault. So the RSS only addresses faults in planner. Yeah.
And I think if you call about Nenads, I think if you have to be very, very safe, you have to be very careful and driving very slowly and so on. So you have to take some chances or risks or something. So it feels strange with this 100% safety.
So all of these are formalized in these rule parameters. So if your assumption is very pessimistic, then you should drive more. AV will drive more conservatively, and vice versa. So the whole point is to formalize the notions of conservativeness versus aggressiveness in these parameters.
Yeah.
Yeah.
And for instance, in Umeå, where the road can be very slippery or icy or something, you have to be very conservative then during winter.
Yeah, that affects your beta min, I think. Yeah.
And just if you look at this picture, I was thinking it was wrong. Like I didn't see that was beta maximum. That was like so it's like does matter regard like this is not beta or regulation regarding beta is like that you're not allowed to brake more than you are, even if you can. That's not that's like something else. So I didn't think in that way. So it's like now it's clear for me how this works.
Oh, I think in terms of beta max, maybe it's not a restriction, but more of a performance parameter. So every company reports their beta max, and the standard takes the largest beta max in defining RSS, right? That could be a possible scenario.
It was more like I thought that you are this formula is calculating the minimum safe distance, but like a car in front of you maybe can't brake fast enough. But it's like I was thinking wrong way. So it's like it doesn't apply here.
Well, in this case, the rear car is worried about the front car braking too hard. That's what causes the rear-end collision. But so
yes, and I didn't realize that it was like sorry. So my question was in wrong direction.
okay, yeah. So yeah, from the regulation perspective, I think alpha max should be a constraint given to the OEMs, whereas the beta max should be more of a collection of different beta maxes from different OEMs and taking the maximum. Yeah, that's probably a reasonable explanation. Yeah.
Yeah. Okay. Thank you.
Okay, so it's almost 5. Any more discussions? Okay, so for those who are late, I discussed the project a little bit. And I changed the assignment to my GitHub, and you can open this iPad notebook to work on the project. So yeah. Okay, that's it for today. Goodbye.
Goodbye and see you.
Yeah.
Thank you. Bye.